On the afternoon of May 25th, 1979, at the beginning of Memorial Day weekend, American Airlines Flight 191 crashed near Chicago's O'Hare International Airport, killing all 258 passengers and 13 crew members aboard, as well as 2 people on the ground. A total of 273 fatalities. In 31 horrifying seconds, America's deadliest aviation disaster unfolded as witnesses watched a massive engine tear away from the wing during takeoff, sending the DC-10 rolling inverted before plunging into an open field. The crash would expose a deadly combination of flawed maintenance procedures, design vulnerabilities, and a cascade of system failures that left experienced pilots powerless to save their own aircraft. But before we get into this video, if you guys want to see more disasters and airplane crash investigations, be sure to like and subscribe. And with that said, let's get straight into the video. It was a bright, clear day in Chicago. Perfect flying weather. On the 25th of May 1979, 258 passengers boarded American Airlines Flight 191 to Los Angeles, a McDonnell Douglas DC-10, and the cabin was filled with holiday travelers, families heading to Southern California for a vacation, business executives attending a publisher's conference, and others simply looking forward to a long weekend. Among the passengers were entire families excited about their trips. The mood was festive, typical of a holiday weekend departure. Nobody aboard could have imagined that their flight would barely make it past the end of the runway. The aircraft operating as Flight 191 was the McDonnell Douglas DC-10-10. The DC-10 was a wide-body trijet, meaning it had 3 engines, one under each wing and one mounted on the tail. This particular aircraft had been in service since 1972 and had accumulated approximately 20,000 flight hours. In command was 53-year-old Captain Walter Lux, a veteran pilot who was type-rated on at least 8 different airliners and who had more than 22,500 flight hours. Captain Lux was a highly experienced and well-respected pilot within American Airlines. Assisting him in the cockpit was 49-year-old First Officer James Stillard and 56-year-old Flight Engineer Alfred Udovich, who together possessed an additional 24,000 flight hours. This was an exceptionally experienced flight crew. Veterans who had handled countless emergencies and challenging situations throughout their careers. Their combined experience totaled over 46,000 flight hours. Under normal circumstances, this level of expertise would be more than sufficient to handle any emergency. But the situation they were about to face was anything but normal. At approximately 3 p.m. Central Daylight Time, Flight 191 was cleared for takeoff from runway 32 right. The DC-10 began its takeoff roll down the 10,000-foot runway, accelerating normally. Everything appeared routine. The 3 Pratt & Whitney engines roared at full power as the aircraft gained speed. Halfway down the runway at 5,000 feet, the plane reached the 175 miles per hour needed to take off. As the DC-10 approached rotation speed, the point where the pilot pulls back on the controls to lift the nose, something catastrophic occurred. As the McDonnell Douglas DC-10 was taking off on the runway, its left engine detached from its wing, causing a loss of control. The massive engine and pylon assembly, weighing approximately 9,000 pounds, separated from the left wing, flipped over and over the wing's leading edge and crashed onto the runway behind the accelerating aircraft. On the cockpit voice recorder, one of the pilots was heard saying "damn" after a loud thunk, the sound of the engine separation. It was the last word captured before the aircraft's electrical systems failed and the recorder stopped functioning. What happened next was captured in a series of remarkable photographs taken by Michael Laughlin, a 24-year-old student pilot who was on a layover at O'Hare. Laughlin had his camera with him and was photographing aircraft when Flight 191 began its takeoff roll. His photographs would become crucial evidence in the investigation. The dramatic images showing the left engine missing from the wing, white vapor trails of fuels and hydraulic fluid streaming from the damaged wing, and the aircraft in its final moments of flight. Unknown to the pilots, the engine separation had triggered a cascade of failures that made their situation virtually unrecoverable. When the engine tore away, it took away with it approximately 3 feet of the wing's leading edge. More critically, it severed hydraulic lines that control the leading edge slats on the left wing. The leading edge slats are movable panels on the front of the wing that extend during takeoff and landing to increase the wing's ability to generate lift at lower speeds. On the DC-10, these slats were held in the extended position solely by hydraulic pressure. There was no mechanical lock to keep them extended if hydraulic pressure was lost. And as mentioned earlier, the engine separation severed the hydraulic fluid lines that controlled the leading edge slats on the left wing and locked them in place, causing the outboard slats to retract under air load. With no hydraulic pressure to hold them extended, aerodynamic forces pushed the left wing's outboard slats back into the retracted position. This created an asymmetric configuration that would prove fatal. The right wing still had its slats fully extended, while the left wing's outboard slats had retracted. This asymmetry had two devastating effects. First, the left wing was now producing significantly less lift than the right wing. Second, and more critically, the retraction of the slats raised the stall speed of the left wing. The pilots did exactly what they were trained to do. When an engine fails during takeoff after reaching decision speed, the correct procedure is to continue the takeoff and climb to a safe altitude using the remaining engines. The DC-10 was designed to fly safely on two engines. American Airlines procedures specified that following an engine failure, pilots should maintain the aircraft's pitch attitude as directed by the flight director, an instrument that provides guidance for optimal climb performance, and accelerate to V2 speed, the takeoff safety speed that ensures adequate climb performance with one engine inoperative. The experienced pilots, Captain Walter and First Officer James, knew it was too late to abort the takeoff, but they immediately attempted the correct procedure for climbing on two engines. First Officer Dillard, who was flying the aircraft, followed the flight director guidance and raised the nose. The aircraft began to decelerate from its current speed toward the prescribed V2 speed of 153 knots. But the pilots were flying blind in a critical way. They had no idea that the left wing slats had retracted, and therefore no idea that the stall speed on their left wing had increased. But why didn't the pilots know about the slat retraction? The answer lies in a cascade of electrical failures triggered by the engine separation. The DC-10 incorporates two warning devices that might have alerted the pilots to the impending stall: the slat disagreement warning light, which should have illuminated after the uncommanded retraction of the slats, and the stick shaker on the captain's control column, which activates close to the stall speed. Both of these warning devices were powered by an electric generator driven by the number 1 engine, and both became inoperative after the loss of that engine. When the engine separated, it caused electrical short circuits that tripped circuit breakers and isolated the electrical bus powered by the number 1 engine. This bus supplied power to numerous critical systems. All of these systems went dark the instant the engine separated. The first officer's control column was not equipped with a stick shaker. McDonnell Douglas offered the device as an option for the first officer, but American Airlines chose not to have it installed on its DC-10 fleet. If American Airlines had purchased the optional second stick shaker for the first officer's control column, powered by a different electrical bus, the crew might have received the warning of the impending stall. The slat position indicators in the cockpit went blank. The slat disagreement warning, which would have alerted them that the left and right wing slats were in different positions, never activated. The pilots had no way to know that by following standard procedures and decelerating to V2, they were descending directly into an aerodynamic trap. Flight 191 was airborne for only 31 seconds. After achieving its highest altitude of 325 feet, the airliner pitched down with its left wing struck the ground. At 325 feet above ground level, the left wing entered a full aerodynamic stall with the right wing still generating lift and the left wing producing almost none. The aircraft began rolling rapidly to the left. The pilots applied full right aileron and right rudder, fighting desperately to control the roll, but the aerodynamic forces were overwhelming. The aircraft crashed around 4,600 feet from the end of the runway. The impact occurred in an open field adjacent to a mobile park home just northwest of the airport. The impact and subsequent explosion were catastrophic. The aircraft, still carrying most of its fuel load for the cross-country flight, disintegrated on impact. A massive fireball erupted as thousands of gallons of jet fuel ignited. The explosion destroyed an old aircraft hangar, several automobiles, and a mobile home. 2 people on the ground were killed by the falling debris. Firefighters who arrived at the scene within a couple of minutes of the disaster recalled that it was total devastation. The intensity of the fire was so extreme that the firefighters initially could not approach the wreckage. The heat was so overwhelming and the smoke could be seen for miles. All 271 people aboard were killed, along with 2 more souls on the ground. It remains to this day the deadliest aircraft accident on US soil. The disintegration was so complete that little useful information could be gleaned from the examining wreckage itself. Bodies were burned beyond recognition, requiring forensic dentists to identify victims. Emergency workers marked human remains with numbered flags as they carefully searched for the still smoldering debris. The National Transportation Safety Board, or NTSB, dispatched a GO team to the crash site that evening. The most obvious piece of evidence was still found on the runway, the number 1 left engine that separated from the doomed DC-10. The engine rolled over the top of the left wing during takeoff and was found next to the departure runway. This immediately told investigators that the engine separation had occurred. But the critical question was why. Engine separations are extraordinarily rare events. Modern commercial aircraft are designed so that even if an engine fails catastrophically, it should remain attached to the wing. So something had clearly gone very wrong with the structure that connected the engine to the wing. The investigation revealed that the pylon had been damaged during maintenance performed approximately 2 months before the accident on March 30, 1979. The damage occurred when American Airlines maintenance personnel removed and reinstalled the left engine and pylon assembly. McDonnell Douglas, the aircraft manufacturer, had published specific procedures for removing and replacing engines. The proper method was this 2-step process. You first remove the engine from the pylon, then remove the pylon from the wing. Each step was to be done separately, using specialized equipment to support the components. However, this procedure was time-consuming and labor-intensive. To save time and money, American Airlines, along with some other carriers, had developed an alternate procedure, removing the engine and pylon as a single unit using a large forklift to support the combined weight. In 2 prior cases on Continental DC-10 airplanes in December 1978 and February 1979, the engine/pylon assembly reinstallation had resulted in damage nearly identical to that occurred on the accident airplane. In both events at Continental, the sound of the flange fracturing was heard by the maintenance personnel. These warnings were not reported to McDonnell Douglas or the FAA. The forklift supporting the engine pylon assembly remained in place overnight between shifts, and investigators suspected that the hydraulic pressure in the forklift may have bled off, causing the forks to move slightly. This small movement, combined with improper procedure, caused the forward bulkhead to bend upwards and contact the wing structure above it. The contact created a small fracture on the upper flange of the pylon's aft bulkhead. The fracture was only about 10 inches long, but it was located at a critical structural point. The damage was not visible during routine inspections because it was hidden behind the engine. Over the next following 2 months and about 1,200 flight cycles, the crack slowly propagated through the structure due to the constant stresses of flight. Each takeoff, each landing, each cycle of pressurization added stress to the weakened component. On May 25, 1979, during Flight 191's takeoff rotation, the crack finally caused complete structural failure. The aft bulkhead separated, allowing the entire engine and pylon to pivot upwards and tear away from the wing. Critically, the NTSB concluded that these 2 events at Continental should have been viewed as an indication that the alternate installation procedure was inappropriate. But because they weren't reported beyond Continental Airlines, the industry never learned of the danger. Simulator tests conducted after the accident proved conclusively that the crew had no reasonable opportunity to save the aircraft. Experienced test pilots, knowing in advance what would happen and given multiple attempts, could not prevent the crash when replicating the conditions faced by Flight 191. When pilots followed American Airlines engine failure procedure and decelerated to V2 speed, they lost control every time. On June 6, 1979, 2 weeks after the accident, the FAA suspended the type certification for the DC-10, thereby grounding all DC-10s under its jurisdiction. It was an unprecedented action, the first time the FAA had ever grounded an entire aircraft type. The grounding included an air regulation that prevented foreign DC-10s from flying into US airspace. The grounding was prompted by the discovery that several other airlines had also been using the unapproved forklift procedure, and inspections revealed cracks in the other DC-10 pylons. American Airlines Flight 191 remains the deadliest aviation accident in United States history. The crash demonstrated how seemingly minor maintenance errors can have catastrophic consequences, how cost-cutting shortcuts can prove fatal, and how a cascade of failures can overwhelm even the most experienced crews. The pilots of Flight 191 did everything right according to their training and procedures. They followed the prescribed actions for an engine failure during takeoff. But they were trapped in an impossible situation. Following proper procedures led them directly into an uncontrollable aerodynamic condition they couldn't see, couldn't detect, and couldn't recover from. The tragedy exposed fundamental vulnerabilities in the DC-10's design, particularly the lack of mechanical lock for the leading edge slats and the single point of failure in the warning systems. It revealed how inadequate regulatory oversight allowed dangerous maintenance procedures to spread across multiple airlines. It showed how poor communication prevented warning signs from being shared and acted upon. The safety improvements that emerged from the disaster, stricter adherence to approved maintenance procedures, better regulatory oversight, improved aircraft design standards, and mandatory reporting systems have made aviation significantly safer. These measures honor the memory of all of those who died on that day and prevent similar tragedies in the decade since. But today, the bricks bearing 273 names stand at the memorials, a permanent reminder that aviation safety is never an accident. It is achieved through rigorous procedures, constant vigilance, and the hard lessons learned from past tragedies. March 27th, 1977. What began as a routine day turned into the deadliest aviation disaster in history. Two Boeing 747s, KLM Flight 4805 and Pan Am Flight 1736 collided on the runway at Los Rodeos Airport in dense fog. In just moments, 583 lives were lost. This is the Tenerife disaster. Earlier that day, a bomb threat at Las Palmas Gran Canaria Airport forced multiple diversions to the small, ill-equipped Los Rodeos Airport. This airport's single runway and minimal infrastructure had no parallel taxiways, which led to a traffic jam of massive aircraft. As darkness settled and fog rolled in, visibility plunged. Pilots and the control tower relied entirely on radio. A garbled instruction combined with cross transmissions created fatal confusion. Multiple voices overlapped, and amidst it all, control clearance blurred with assumed permission. Meanwhile, Pan Am was still on the runway, and KLM began its takeoff roll. At 17:06, KLM began its takeoff roll. Just meters ahead was Pan Am still on the runway. The impact tore through Pan Am's fuselage, and both planes erupted in a fiery inferno. All 248 people on board KLM perished, and Pan Am only saw 335 fatalities. Only 61 survived, many escaping through a ruptured fuselage near the wing. But how did we really get here, having two Boeing 747s crash into each other on a runway? So let's set the stage back in Canary Islands in 1977. It was a quiet Sunday on the Canary Islands, a popular holiday destination off the coast of Africa. Normally, Los Rodeos Airport on Tenerife was a sleepy regional airfield handling small domestic flights and the occasional international arrival. But that day, chance and tragedy would converge in ways no one could have foreseen. Earlier that afternoon, planted by the separatist group ETA exploded at Gran Canaria's Las Palmas Airport. Although no one was killed, Spanish authorities quickly shut the airport down to search for additional explosives. This single decision, routine in such circumstances, unleashed a very bad domino effect. Dozens of incoming aircraft, including two giant queens of the sky, the Boeing 747s of KLM and Pan Am, had to divert to Tenerife's Los Rodeos Airport. A small airport not designed for such heavy traffic suddenly became gridlocked with the massive wide-body jets. Los Rodeos had only one runway, and a single narrow taxiway at that. Once aircraft landed, they were forced to backtrack along the runway to reach the terminal. Parking space was limited, and within an hour, jumbo jets from across Europe crowded the apron, forcing crews and controllers into an unusual, sometimes improvised procedures. Among them were KLM Flight 4805 from Amsterdam and Pan Am Flight 736 from Los Angeles by the way of New York. These two aircraft, each weighing over 300 tons fully loaded, were never meant to meet here, let alone share the same strip of tarmac in near zero visibility. KLM passengers, mainly Dutch tourists, waited on board as the crew decided to refuel at Tenerife rather than risk further delays at Las Palmas later. The refueling alone cost nearly 35 minutes. Meanwhile, 396 of the Pan Am passengers remained seated for hours, frustrated, confined, and restless. Both aircraft crews were under mounting pressure, Pan Am eager to get moving, KLM conscious of Dutch duty hour regulations that restricted how long pilots could legally fly before resting. By late afternoon, another complication set in. A thick blanket of fog descended over Los Rodeos, a common occurrence due to its elevation and proximity to the mountains. Visibility, already limited, dropped to a few hundred meters. Controllers in the small tower could barely see the runway. Pilots in the cockpit could not see each other's aircrafts nor the tower. Tenerife also had no ground radar to track aircraft movement. Communication would now rely entirely on voice through radio transmissions, already crackling with static and overlapping signals. Shortly after 5 p.m., the weather closed in. Pan Am received instructions to taxi along the runway and to exit at the third taxiway, and then circle around to the terminal for departure. At the same time, KLM was instructed to taxi down the same runway, make a 180-degree turn at the far end, and then position itself for takeoff. But the taxiways at Los Rodeos were poorly marked, narrow and at odd angles. In the fog, Pan Am's crew struggled to find their designated exit. They missed the first two runoffs, searching for the third. The KLM, meanwhile, reached the runway threshold, turned around, and waited, its engines already spooling and its captain eager to depart. Now, inside KLM's cockpit sat Captain Jacob van Santen, one of the airline's most experienced and respected pilots, a training captain and the face of KLM's advertising campaigns at the time. And because of the high regard that he was kept to, he was always pressured to maintain a schedule. And because of the delays, he was becoming impatient. The co-pilot and flight engineer voiced caution, but hierarchy in the cockpit culture of the 1970s meant that challenging the captain outright was very rare. Radio transmissions grew increasingly confusing. Controllers' instructions overlapped with Pan Am's position reports. Words like OK, stand by, and you are cleared filled the airways. But the messages weren't always clear who they were meant for. At 5:06 p.m., the fog was at its thickest. The Pan Am Jumbo was still lumbering down the runway, searching for its exit. The KLM, now fully loaded with fuel, sat at the far end, poised for takeoff. A garbled transmission from the tower, and Pan Am was misheard by the KLM crew. The captain believed he had clearance. His co-pilot, hesitant, attempted to clarify, but Van Zeten's authority was absolute. He pushed the throttles forward. The runway, choked in fog, now held two aircraft of unprecedented size, hurtling toward the inevitable. Two 747s carrying nearly 650 people now found themselves lined up on the same fog-covered runway, a single strip of asphalt, one preparing to depart and the other taxiing straight towards it. The stage was set for a disaster unlike anything aviation had ever seen. The nose of KLM Flight 4805 sliced into Pan Am 736. In an instant, the Dutch jumbo jet undercarriage ripped open the upper fuselage of the Pan Am aircraft. The sound was like an explosion, twisting metal, breaking glass, and the sudden roar of igniting jet fuel. The Pan Am jet was torn apart, the roof split open, flames shot through the cabin, and hundreds of passengers were thrown into chaos. Many were unfortunately unalived instantly in the forward section. For those still alive, the cabin filled with black smoke so quickly that visibility dropped to almost nothing. Passengers clawed their way toward the light, toward holes ripped in the fuselage. Some were leaping to the tarmac below in desperation. Out of nearly 400 on board, just 61 souls would make it out alive. The KLM aircraft, still carrying a full load of fuel for its journey back to Amsterdam, briefly lifted after the collision, before slamming back down onto the runway. What followed was a firestorm. The explosion consumed the jet in seconds. All 240 passengers and crew aboard perished, trapped in an inferno no human could survive. Emergency services rushed to the scene. But Los Rodeos was utterly unprepared for disaster of this scale. Fire trucks and ambulances were too few, their access slowed down by the cars that had clogged the airport roads during the earlier bomb scare. The flames, fed by thousands of gallons of jet fuel, were so intense that rescuers could barely approach. In a matter of minutes, both aircrafts, once symbols of modern aviation, were reduced to burning wrecks. What had begun as a day of diversions, delays, and fog ended in the deadliest accident in aviation history. One survivor said, "We all settled back, and the next thing, an explosion took place and the whole port side was just torn open." Investigators from Spain, the Netherlands, and the United States descended on Tenerife. What they faced was unlike anything they had ever seen before. Two Boeing 747s reduced to twisted wreckage, scattered across the runway in dense fog. The blackened debris field stretched hundreds of meters, and the acrid smell of fuel and smoke lingered for days. The first task was grim, recovering the flight recorders, or the black boxes. On the Pan Am jet, the cockpit voice recorder revealed that the frantic last word of the crews as they spotted the KLM aircraft at the final moment. "There he is," followed by the impact. The KLM recorder, however, revealed something even more chilling. Captain Jacob's calm yet mistaken belief that he had been cleared for takeoff. His confident voice contrasted sharply with the confusion echoing through the radio frequencies. Investigators quickly uncovered a critical factor: radio communication problems. Because Los Rodeos Airport had only one radio frequency for ground and air traffic, multiple transmissions overlapped, and at one point the Pan Am crew and air traffic control both responded to the KLM's cockpit at the same time. This resulted in what's called heterodyning, a distortion that cancelled parts of the message. To the KLM crew, it sounded as if they had been cleared for takeoff, but in reality, no such clearance had been given. Additionally, the weather played its part too. The thick, shifting fog that had blanketed the runway reduced visibility to almost nothing. Neither crew could see the other until it was far too late. At one point, Pan Am's captain asked for confirmation about taxiing, but the fog and the poor airport signage made navigation nearly impossible. Even seasoned pilots found the runway layout confusing under these conditions. The investigation also highlighted human factors. Captain Van Zanten wasn't just any pilot. He was KLM's chief flight instructor, the face of the airline's training program. He even featured in advertisements as the epitome of professionalism. His reputation made it nearly impossible for his first officer or flight engineer to openly challenge him. When the flight engineer timidly suggested that the Pan Am might still be on the runway, Van Saturn dismissed it. And seconds later, the disaster unfolded. This exposed a dangerous truth. The airline culture at the time was deeply hierarchical, often preventing junior crews from speaking up. The real report painted a complex picture. The KLM's captain's premature takeoff was identified as a direct cause. But investigators emphasized that the chain of circumstances that set the stage, the bomb threat in Gran Canaria, the sudden diversion to Tenerife, the crowded single runway airport, the thick fog, the radio interference, and the lack of clear ground radar. However, the tragedy wasn't in vain. Out of this catastrophe came sweeping changes to aviation safety. The concept of crew resource management, otherwise known as CRM, was born. A new training philosophy that encouraged open communication, teamwork, and the ability for any crew member, no matter their rank, to question a captain's decision if safety was at stake. Today, CRM is standard across airlines worldwide. Airports too learned their lessons. Runway markings and signage were standardized. Ground radar was installed at major airports, and stricter international phraseology was introduced in aviation. Communication to reduce ambiguity. Pilots were trained to never use casual phrases like "we are at takeoff," but instead speak standardized terms. The Tenerife investigation, though devastating, reshaped aviation forever. The lessons learned from those smoldering wrecks still echo in every cockpit and control tower to this day. On March 27, 2007, 30 years later, a memorial was erected atop Mesa Mota, an 18-meter spiral staircase titled "The Stairway to Heaven" by Rudy Van de Wint. It is an endless ascent cut short, symbolizes the lives interrupted yet seeking peace. Tenerife's tragedy remains a solemn testament to the cost of miscommunication. But through loss, aviation grew safer, evolving with empathy, precision, and teamwork. We remember the 583 lives lost not just with sorrow, but with a commitment to vigilance in every flight. May the memory guide us to clearer skies. On the morning of December 29th, 2024, Jeju Air Flight 2216 approached the quiet coastline of South Jeolla Province. It had been an entirely ordinary international flight, an overnight journey from Bangkok to South Korea that thousands of travelers make every week. On board the Boeing 737-800, families were preparing for winter holidays, students were returning home, and workers were heading back after their year-end vacation season. There were 181 people on board, 175 passengers and 6 crew, unaware that they were minutes from one of the most deadliest aviation disasters in South Korean history. But in order to truly understand how this devastating disaster came true, let's set up the scene. There are 2 types of airport obstruction standards in aviation. The first, set by the International Civil Aviation Organization or ICAO, which requires that any equipment within 240 meters of a runway end must be frangible, meaning it's supposed to be designed to brake on impact. The second, recommended by the United States FAA, goes further. A larger runway safety area, arrestor systems for shorter runways, and breakable materials for all obstacles near the runway. At Muan International Airport in South Korea, an instrument landing system localizer or ILS localizer sat on top of a concrete embankment. 2 meters tall, solid concrete, located exactly 250 meters from the runway end, just 10 meters outside the ICAO's frangible zone. Technically compliant, but practically deadly. On December 29, 2024, that 10-meter loophole would kill 179 people. This is a true story of Jeju Air Flight 2216. According to regulations, airports with fewer than 5,000 flights per year need only 2 bird alert team members. Muan had 4 on paper. They worked in rotating shifts. 2 during the day, and 1 at night. And on the morning of December 29, 2024, at 8:57 a.m., as the shift change approached, one person was on duty. One Batman, as they're called locally, one person with a firearm and radio responsible for monitoring 13 kilometers of wetland habitat, one person to watch for Baikal teals, and thousands of other water birds that winter on Korea's southwestern coast. At larger airports like Incheon, Gimpo, Jeju, there are 40, 23, and 20 bird alert team members respectively. At one, excluded from plans to boost staffing due to its low raw numbers, there was just one. 3 elements: a concrete barrier 10 meters outside the frangible zone, the highest bird strike rate in South Korea, and a single person on bird control duty during a shift change. December 29, 2024 was an accident waiting to happen. At 2:29 local time, Bangkok, Jeju Air Flight 2216, a Boeing 737-800 registered as HL8088, departs from Suvarbami International Airport, its destination Muan. The aircraft is just 15 years old, previously operated by Ryanair, and acquired by Jeju Air in 2017. It's been flying for Jeju Air for nearly 8 years, powered by 2 CFM International CFM56 engines, the workhorse of the 737 fleet. On board are 175 passengers, 6 crew, 173 Koreans, and 2 Thai nationals. Many are families returning home from Christmas holidays. The youngest passenger is just 3 years old. This is Jeju Air's 4th weekly flight on the Muan-Bangkok route, a service that resumed less than a month ago after the COVID-19 suspensions. The airline is just 19 years old, and in those 19 years, 0 fatal accidents until that fateful day. The flight proceeds normally, across the South China Sea, over Vietnam, and through Chinese airspace. 6.5 hours of routine operations. At 8:57 a.m., Flight 226 began its descent into Muan. The crew is cleared for an approach onto runway 01, a straightened approach from the south, landing gear down, flaps extended, standard configuration, everything by the books. At 8:57 a.m., Air Traffic Control broadcasts a warning: bird activity in the area. Routine for the area. Muan's controllers issue this warning regularly. The wetlands guarantee it. A minute passes. At 8:58 a.m., impact. The pilots report a bird strike, mayday, mayday, mayday. But what happens next depends on who you ask. The crew initiates a go-around. Standard procedure: retract the flaps, retract the landing gear, climb, assess. In the cockpit, alarms warning: the right engine is damaged, flames visible on the external cameras. The left engine unclear. But they have a decision to make, and they have seconds to make it. At 8:59 a.m., the crew requests runway 19, the opposite direction. The same strip of asphalt, approach from the north instead of the south. The aircraft enters a teardrop turn. Steep descent, 180-degree reversal to line up with runway 19. During this turn, something happens. The flight recorders, both the cockpit voice recorder and flight data recorder, stop recording. At 8:58 a.m., both black boxes go silent. Complete electrical failure. Loss of power to the recorders, the backup power designed to prevent exactly this scenario also fails. For the next 4 minutes, there is no official record of what happened in that cockpit. At 9:02 a.m., Flight 2216 touches down on runway 19. No landing gear, a belly landing. The aircraft makes contact 1200 meters past the threshold, nearly halfway down a 2800 meter runway. At touchdown, the 737 is traveling far faster than normal landing speeds. Video from the airport shows the plane streaming down the runway, sparks erupting from the fuselage. No thrust reversers, no spoilers, no wheel brakes, just friction between the aluminium and concrete. The nose drops, the tail drags, metal grinding against the asphalt. The plane begins to slow, but not nearly enough. At 9:03 a.m., Flight 2216 reaches the end of runway 19, still traveling at a high speed. The aircraft crosses the threshold, into the grass, through the approaching lighting system, and toward the embankment 250 meters away, which was set 10 meters outside the frangible zone. The impact is instantaneous. The nose crumbles, The cockpit compresses and the fuselage ruptures. Jet fuel ignites and the fireball is visible from kilometers away. Of 181 people on board, only 2 survive, both flight attendants seated in the rear galley, the furthest point from the impact. At 12:30 p.m., fire officials announced that all passengers except 2 were rescued are presumed to be dead. And by the evening, the death toll is confirmed. 179 dead, 83 women, 82 men, and 11 bodies so unrecognizable that identification will take weeks. This is now South Korea's deadliest aviation disaster, surpassing the 2002 Air China Flight 129 crash that killed 129 people. It's the deadliest accident involving a South Korean carrier since Korean Air Flight 801 in 1997. It's also the deadliest runway excursion in aviation history. And it's the deadliest single aviation accident since Lion Air Flight 6110 in 2018, which recently has been surpassed by Air India Flight 171. For Jeju Air, a low-cost air carrier, it's their first fatal accident in the airline's history. On January 7, 2025, the Aviation and Railway Accident Investigation Board confirms bird DNA in both engines. Baikal teals, a species of migratory duck, each weighing approximately 0.45 kilograms. Feathers and blood in the right engine, feathers and blood in the left engines, with both engines being struck. The preliminary report describes a cascade. Bird strike leads to engine damage leads to hydraulic failure prevents landing gear deployment. The crew, dealing with dual engine ingestion and complete electrical failure, did not have time to manually extend the landing gear using the gravity drop system. If only one engine had failed, they might have had enough time. But with both engines damaged, with power lost, and 4 minutes of missing data, the precise sequence remains unclear. Then, in July 2025, the investigation takes a turn. According to the South Korean media, citing unnamed unofficials, the ARAIB has reached a preliminary conclusion. The crew shut down the wrong engine. The right engine, damaged by a bird strike, was indeed failing, but the left engine remained operational. And in the chaos of alarms, warning, and emergency procedures, one of the pilots shut down the left engine, the good one, instead of the right. Dual engine failure, not from bird strikes, but from pilot error. The families of victims reject this conclusion outright. So does the Jeju Air Pilots Union. They point to other factors: the runway slope, the late touchdown point, the concrete barrier. They accuse the ARAIB of scapegoating dead pilots while ignoring systemic failures. This document officially was never released, and as of now, the final report remains unpublished. The question is, as always, whether the accident was inevitable or preventable. In 2023 alone, the FAA recorded 19,400 wildlife strikes at US airports worldwide. From 1998 to 2023, bird strikes with civilian and military aircraft killed 491 people and destroyed 350 planes. About 61% of bird strikes occur during landing. They are, statistically, the most common phase of flight for bird encounters. Commercial pilots hit birds regularly. Small birds, usually cardinals, robins, sparrows, and most strikes cause no damage. Some may cause minor damage, and a few cause millions in repair. But dual-engine bird strikes are exceptionally rare, and catastrophic outcomes come from dual-engine strikes are rarer still. The most famous case of this is US Airways Flight 1549, the Miracle on the Hudson as it's called. January 15, 2009, an Airbus A320 struck a flock of Canada geese shortly after takeoff from LaGuardia. Both engines failed, and Captain Chesley Sullenberger ditched the aircraft in the Hudson River. All 155 people on board survived. It was a miracle, but it was also a ditching in the water and not a runway overrun into concrete. Flight 226 had no river. It had wetlands, yes, but also a runway that ended in grass, approach lights, and a 2-meter concrete wall. Had the crew landed further up the runway, perhaps the outcome would have been different. Had they deployed the landing gear manually, perhaps. Had the barrier been frangible, almost certainly. Had the arrestor cables been present, possibly they could have saved it. But they weren't able to save it because none of these safety features were in place. But what's not debatable here is that a concrete structure 10 meters outside a safety zone killed 179 people. Between the Wright brothers' first flight in 1903 and the year 2023, bird strikes have been a known, quantified, manageable risk. Airports use radar, drones, sound cannons, habitat modifications. Pilot training emphasizes go-around, single-engine operations, and the emergency landing procedures. Aircraft engines are tested against bird ingestion. 4-pound chickens are fired from cannons at cruise speed. The industry has spent billions making air travel safer. And it has worked. Aviation by far is the safest form of transportation. In 2023, the United States recorded over 4,600 workplace fatalities. By comparison, commercial aviation worldwide sees an average about 200 fatalities per year across billions of passenger miles. The math is unambiguous. You are safer in an airplane than in almost any other human activity. But that safety is not inherent. It is engineered, it is regulated, and it is maintained. When it fails because someone, somewhere, decided that 10 meters was enough, that one person was sufficient, and that the concrete was acceptable. 179 people died at Muan because accidents don't happen. They are built one decision at a time. February 4, 2015 began like any other ordinary morning in Taipei. Traffic was steady, the sky was clear, and inside Zhongshan Airport, passengers prepared for TransAsia Airways Flight 235, expecting nothing more than a short 35-minute journey to Kinmen. No turbulence, no complexity, no reason to imagine anything unusual. This was a routine regional flight flown hundreds of times before. The aircraft for today's flight, registered B22816, was an ATR 72-600, one of the newest turboprops in the world at the time. It had been delivered to TransAsia in April 2014, making it less than a year old at the time of the crash. The plane had accumulated only about 1,600 flight hours, a tiny number compared to the tens of thousands that most commercial aircraft accumulate over their lifetime. It was considered modern, efficient, and technologically advanced for its time. Almost no one at the airline imagined that this particular aircraft would become the subject of global scrutiny. 3 pilots occupied the cockpit that morning. Captain Liao Xian-song, age 42, was a pilot in command. He had 4,914 total flight hours, but only 250 hours on the ATR 72-600, the newest variant. He had previously flown the earlier ATR 500 series, but transitioning to the new -600 model required new training. His records later revealed a worrying detail. He had struggled in simulator checks involving engine failures. In fact, he had failed the very scenario more than once. The airline documented this. However, he remained in active service. Beside him sat First Officer Liu Shangxian, age 45. He actually had more total flight experience than the captain, around 6,922 hours, with over 3,100 hours on the ATR aircraft. He had experience, familiarity, and a calm reputation. But as first officer, he was not the one making the final decisions that morning. Additionally, on board was a third pilot. A flight trainee, Hung Ping-chong, age 63, occupied the jump seat. He was observing to gain operational experience. Although he had substantial time as a military and civilian pilot, he was not actively manipulating the controls at the time of the accident. His presence added another dynamic in the cockpit. 3 people, 3 levels of authority, something that has complicated decision-making in other incidents throughout aviation history. Together, these 3 men would face a scenario that demanded absolute clarity. But just 23 seconds after takeoff, the calm inside the cockpit was shattered. One of the warning systems triggered, indicating the right engine, engine number 2, was losing power. It wasn't dramatic failure. There was no fireball or explosion. In fact, many aircraft experience a single engine loss and continue flying safely. But this moment required precision, clarity, and strict adherence to procedure. The aircraft could easily have returned for an emergency landing if everything had gone right. Instead, confusion began to take over. Inside the cockpit, the captain reacted quickly. Too quickly. Believing the left engine was the one failing, he pulled back the throttle on engine number 1, the only engine that was still functioning normally. The ATR suddenly found itself with almost no usable thrust from either engine. The aircraft began to lose speed, and once speed drops below a critical point, even a perfectly functional plane becomes aerodynamically unstable. Warning alarms erupted. The stick shaker activated, signaling an impending stall. The aircraft was climbing but slowing rapidly. The first officer noticed something was wrong and questioned the captain's decision. But by then, so much power had already been pulled that the situation was becoming irreversible. The aircraft was now barely staying in the air. Meanwhile, down on the ground, Taipei continued moving through its day, unaware of what was happening above. Drivers crossed the Nanhu Bridge, a busy elevated roadway spanning the Keelung River. Among them was a taxi driver whose dashcam would unintentionally record one of the most shocking aviation clips ever seen. As Flight 235 descended through the low skyline, the aircraft appeared sideways in the dashcam's frame. It wasn't flying so much as gliding nose up, desperately trying to stay aloft. Its left wing dipped and then dipped again, coming dangerously close to the buildings and the cars below. And then, in a single unforgettable moment, the aircraft's left wing struck the side of the bridge. It sliced through the edge barrier, clipped the front of a passing taxi, and tore itself apart as the aircraft rotated violently before crashing into the Keelung River. What was once a routine morning flight had collapsed into chaos in front of thousands of unsuspecting commuters. The footage spread around the world within hours. People were stunned, not only by the crash itself, but by the eerie clarity of the final seconds. Rescue teams arrived almost immediately. Large pieces of the fuselage were still floating above the river's surface, while other sections had sunk into the cold, muddy water. Passengers were trapped in their seats. Some were unconscious, others desperately trying to hold on to any floating debris. Out of the 58 people on board, only 15 were pulled out alive. As investigations began, the dashcam footage alone couldn't tell the full story. The black boxes, however, revealed every detail with painful clarity. Engine number 2 had suffered a sudden loss of power shortly after takeoff. The warnings were clear. The instruments were clear. Yet inside the cockpit, the crew misidentified the failed engine and shut down the wrong one. With no effective thrust from either engine, the aircraft stalled and lost lift. The pilots attempted to restart the functioning engine, but by the time they realized the mistake, there wasn't enough altitude or time left to recover. The crash shocked the aviation world. Regulators across Asia tightened screening and training standards. TransAsia grounded all ATR pilots for retesting, and several failed the checks. The airline, already under pressure, eventually shut down entirely the following year. The footage of Flight 235 became part of safety courses and aviation classrooms around the world, a stark reminder of how quickly a misunderstanding can escalate into a disaster. Flight 235 will always be remembered not just because it crashed, but because the world saw it happen. The video captured the vulnerability of flight in a way that no report or diagram ever could. It forced investigators, airlines, and the public to confront what really happened in those 2 minutes and 20 seconds after takeoff. Today, the footage remains difficult to watch, not because of the shock factor, but because of the awareness that this tragedy was preventable. Behind every frame is the story of a mistake that grew too large, too fast, and cost too many lives. On the evening of August 12, 1985, families across Japan were preparing to celebrate Obon, a cherished Buddhist holiday, for visiting relatives and honoring ancestors. Tokyo's Haneda Airport bustled with travelers heading home, and among the dozens of flights departing that evening was Japan Airlines Flight 123, bound for Osaka. It was a routine domestic flight that would take just 54 minutes. However, nobody could have imagined that this flight would become the deadliest single aircraft accident in aviation history. But before we get into this video, I would really appreciate it if you guys could give it a like and subscribe if you want to see more content like this. And with that said, let's get straight into the video. The aircraft operating this flight was a Boeing 747 SR-46. The SR designation stood for short range, a variant specifically designed for Japan Airlines to handle unique demands of Japan's domestic market. Unlike the standard 747s built for long international flights, this aircraft has been reinforced with a stronger fuselage and a more robust landing gear to withstand the constant stress of frequent takeoffs, landings, and pressurization cycles on the short routes between Japanese cities. At the time of the accident, the airplane had accumulated a total flight time of 25,000 hours and 18,000 landings. For Boeing 747, this represented intensive use over its 7-year service life. In the cockpit that evening sat 3 experienced aviators. Captain Masami Takahama, age 49, served as a training instructor, having logged about 12,000 flight hours, including about 4,800 flight hours on the type. First Officer Yutaka Sasaki, age 39, was undergoing training for promotion to captain and flew Flight 123 as one of his final training flights, acting as a captain while sitting in the left seat. Flight engineer Hiroshi Fukada, age 46, was a veteran with about 9,000 flight hours, including 3,800 hours on the type. The aircraft's cabin was configured in a high-density layout to maximize capacity on this popular domestic route. On this particular evening, the flight was carrying 524 people, 509 passengers, and 15 crew members. The plane was nearly at capacity, with families, business people, and off-duty airline employees all traveling during the holiday rush. Among the passengers was 26-year-old Yumi Oichi, an off-duty Japan Airlines flight attendant returning home to Osaka to visit her family. She had recently married and loved her career with the airline. On this flight, she was simply a passenger, seated in row 56 near the rear of the aircraft. At 6:12 p.m., Flight 123 took off from Haneda Airport bound for Osaka's Itami Airport. The departure was unremarkable. The 747 climbed smoothly into the evening sky, beginning its ascent towards cruising altitude. The passengers settled into their seats, some reading magazines, others gazing out at Tokyo's sprawling cityscape shrinking below. Approximately 12 minutes after takeoff at an altitude of 24,000 feet, at an airspeed around 300 knots, a bang and vibration and cabin decompression was recorded on the cockpit voice recorder. Yumi Aoichi later recalled, "I was reading a magazine in 56C seat. The atmosphere around the rear part of the plane was unchanged from usual. At 6:25, there was a loud crash from overhead and my ears hurt." She described how the interior of the cabin suddenly became all white and oxygen masks immediately dropped from the ceiling. What passengers and crew couldn't see was a catastrophic structural failure occurring at the rear of the aircraft. The aft pressure bulkhead had ruptured, and the pressurized air in the cabin blew out into the aft fuselage, blowing off the auxiliary power unit or APU and portions of the tail cone, forcing considerable part of the vertical stabilizer to break off. At the same time, all 4 hydraulic systems were severed, making the flight control surfaces inoperable. The vertical stabilizer, the large vertical tail fin that provides directional stability, had been blown away. Without it and without hydraulic control, the aircraft was essentially uncontrollable. At 46 seconds after decompression, the captain signaled an emergency on the transponder and requested a return to Tokyo. 32 minutes of struggle. What followed was an extraordinary display of skill, determination, and courage under impossible circumstances. The crew found themselves piloting a crippled aircraft with virtually no directional control. The 747 began to oscillate wildly in what pilots call a phugoid cycle, a rhythmic pattern of climbing and descending, combined with a severe Dutch roll, where the aircraft swayed side to side like a ship in the storm. The combined phugoid and Dutch roll caused the plane to fly like a ship on a storm-tossed sea, rising and falling, rolling and plunging, swaying back and forth as it staggered forward, unstable on every axis of motion. In the cabin, terror gripped the passengers. The violent motions threw people against the restraints. Loose items flew through the air. Some passengers, realizing the gravity of the situation, began writing farewell messages to their loved ones. In the cockpit, Captain Takahama and his crew worked desperately to control the aircraft using only the engines, varying thrust on the left and right side to steer the massive jet. It was an incredibly difficult technique that few pilots had ever attempted outside of simulators. Tokyo Control contacted the aircraft and asked the nature of the emergency. At this point, hypoxia appeared to have begun setting in, as the pilots did not respond immediately. The captain and co-pilot asked the flight engineer repeatedly if hydraulic pressure had been lost, seemingly unable to comprehend it. Only then did the captain report that the aircraft had become uncontrollable. Uncontrolled, Captain Takahama reported to air traffic control, a chilling two-syllable word that conveyed the dire situation. For 32 agonizing minutes, the crew fought to save their aircraft and everyone on board. They tried everything, adjusting the engine power, attempting to maintain altitude, desperately seeking a place to attempt an emergency landing. The aircraft continued to fly with severe Dutch roll and phugoid motions for about 32 minutes. Years later, aviation experts would attempt to recreate the scenario in flight simulators. None could keep the aircraft aloft for even half of the time that Captain Takahama and his crew managed. Their skill and determination were nothing short of remarkable. But unfortunately, physics and engineering have their limits. The crash. Finally, at about 6:56 p.m., the aircraft crashed into the south ridge of Mount Takamagara, also known as Mount Osutaka. Towering over 1,500 meters high near Ueno village, the impact was devastating. The flight hit Mount Osutaka at a speed of 340 knots, or more than 391 miles per hour. The Boeing 747 disintegrated on impact, scattering wreckage across the mountainside. The crash site was in an extremely remote and treacherous location, accessible only by helicopter or by foot through difficult mountain terrain. The crash was attributed to a missing tail fin that was likely structurally weakened because of frequent landings and takeoffs. Not until 14 hours after the crash were emergency crews able to reach the area. A Japan Self-Defense Forces helicopter spotted the crash after nightfall, but couldn't land due to poor visibility and mountain terrain. The pilots reported seeing no signs of survivor in the air. The decision was made to wait until morning to launch a full ground rescue operation. This delay, however, would prove tragic. Medical staff had found 4 survivors out of 524 passengers in the debris. They also had identified bodies with such injuries that suggested many had died from shock and overnight exposure. One doctor said that if the discovery had come 10 hours earlier, we could have found more survivors. The 4 survivors were all female passengers seated in the last 7 rows of the aircraft, the only section that remained relatively intact. They were Yumi Oichi, a 26-year-old off-duty flight attendant, 12-year-old Keiko Kawakami, and mother and daughter Hiroko and Mikikoko Yoshizaki. Yumi Oichi was trapped in row 56 and lived for another 16 hours overnight until rescue. She woke when the rescuers shouted, "You are all right now," and pulled her from the wreckage. She had a fractured pelvis and arm. Oichi said she recalled bright lights and helicopter sounds shortly after waking up amidst the wreckage. She could hear screaming and moaning from other survivors, but the sounds gradually died away throughout the night. This heartbreaking testimony confirmed what investigators suspected, that an estimated 20 to 50 passengers had actually survived the initial crash, but died from their injuries while awaiting rescue. Keiko Kawakami, 12 years old and the only survivor from her family of 4, was found hanging from the branches of a nearby tree. She had been catapulted out of her seat when the airliner hit the mountain and landed on top of a nearby bush. While she suffered extensive injuries and had to be treated at a hospital for 3 months, she fully recovered, though she lost both her parents and her younger sister in the crash. The toll was unimaginable. The crash had killed all 15 crew members and 505 of the 509 passengers on board. The investigation. Japan's Aircraft Accident Investigation Commission, assisted by the US's NTSB and Boeing, launched an extensive investigation. What they discovered was, quite frankly, shocking. This disaster had been 7 years in the making. On June 2, 1978, the airplane experienced a severe tail strike incident during landing at Osaka, Japan. Several aft fuselage frames, skins, and the aft pressure bulkhead were substantially damaged. At the time, the airplane had 6,200 hours and 12,000 cycles, and required significant repairs. Boeing dispatched an airplane on-ground team to perform the repairs. The job was complex. They needed to replace the damaged lower half of the aft pressure bulkhead. The correct repair procedure called for a single continuous splice plate with 3 rows of rivets to join the new section to the existing structure. But the Boeing team had made a critical error. The subsequent repair of the bulkhead did not conform to Boeing's approved repair methods. Boeing's repair procedure calls for 1 continuous splice plate. Instead, the Boeing's team used 2 splice plates, one above the other, with only 2 rows of rivets connecting each plate to the bulkhead. This modification had devastating consequences. A review after the Flight 123 crash determined that this decreased the strength of the area by about 70%. With only 70% of the required strength, the repair was, quite frankly, a time bomb. The single middle rivet row became the origin of structural fatigue cracking. These cracks connected rivet to rivet and propagated through the crack stop straps. The modified splice error could not be found through visual inspections since the gap was filled with fillet sealant. During the investigation, the Accident Investigation Commission calculated that this incorrect installation would fail after about 11,000 pressurization cycles. The aircraft had accomplished 12,318 successful flights from that time, from the time that the faulty repair was made to when the crash happened. So every flight, every pressurization cycle added stress to those fatigue cracks. They grew slowly and invisibly, hidden beneath the sealant. And on August 12, 1985, during Flight 123's climb to cruising altitude, the weakened bulkhead finally gave way. The aftermath. The disaster devastated Japan. The crash is the deadliest single aircraft accident in aviation history and remains the deadliest aviation incident in Japan. The president of Japan Airlines at the time, Yasumoto Takagi, assumed responsibility for the accident and resigned. The company's maintenance manager, Hiro Tominaga, tragically committed suicide. Boeing also acknowledged its responsibility in the faulty repair. The investigation led to significant changes in aviation safety. On May 26, 1987, the FAA issued AD 87-12-04 to require installation of a hydraulic fuse in the number of 4 hydraulic systems on Boeing Model 747 series airplanes. Additionally, it required inspection for damage and cracking of the aft pressure bulkhead on other Boeing Model 747 airplanes. These directives were later strengthened with additional repetitive inspection requirements. The accident also influenced future aviation incidents in unexpected ways. In 1989, United Airlines Flight 232 experienced a complete loss of hydraulic control after an engine failure. The Czech pilot aboard that flight, Dennis Fitch, had studied the JL123 case and practiced similar scenarios in simulators. His knowledge contributed to the crew's ability to perform a controlled crash landing that saved 184 out of the 296 people aboard. In 2006, the Safety Promotion Center opened on the grounds of Haneda Airport. This center was created for training purposes to alert employees to the importance of airline safety and the responsibility to ensure safety. The center has displays regarding aviation safety, the history of the crash, and selected pieces of the aircraft and passenger effects, including handwritten farewell notes. Families of the victims, together with local volunteer groups, hold an annual memorial gathering every August 12th near the crash site in Gunma Prefecture. The mountain path to the crash site has been improved to allow visitors to pay their respects. The 3 cockpit crew members, Captain Takahama, First Officer Sasaki, and flight engineer Fukada were awarded the Polaris Award in 1987 for their extraordinary efforts to save the aircraft and their passengers. Aviation experts worldwide recognized their 32-minute struggle to control an essentially uncontrollable aircraft as one of the most remarkable displays of airmanship in aviation history. Today, Japan Airlines Flight 123 stands as a somber reminder of how a single maintenance error can have catastrophic consequences years later. It underscores the critical importance of following proper repair procedures, conducting thorough inspections, and maintaining the highest standards of aviation safety. The 520 people who perished on that August evening were not statistics. They were fathers and mothers, sons and daughters, colleagues and friends. They were people returning home for the holidays, traveling for business, visiting loved ones. Their loss forever changed hundreds of families and an entire nation. The 4 survivors carried forward the burden of survival, each bearing physical and psychological scars that would last a lifetime. The captain's daughter, Yoko Takahama, who was a high school student at the time of the crash, went on to become a JAL flight attendant, honoring her father's memory by dedicating her career to the same airline and the same passengers he had tried so valiantly to save. Every year on August 12th, as the sun sets over Mount Takamagahara, those who remember make the pilgrimage to the crash site. They climb the mountain paths, they light incense, they leave flowers, and they remember the 520 lives cut short, and 3 pilots who fought until the very end to bring them home safely. Japan Airlines Flight 123 reminds us that aviation safety is built not just on technology and regulations, but on human vigilance, proper procedures, and the understanding that even the smallest error can have unimaginable consequences. It is a legacy written in sorrow, but one that has made aviation safer for millions of passengers in the decade since. Thank you so much for watching this video. If you would like to see more videos, YouTube thinks you should watch the video on screen right now. If you'd like to see more plane crash videos, you can check out my playlist here. And if you have any suggestions for future videos, be sure to leave them in the comments section down below. And if you like this video, be sure to like and subscribe. And with all that said, I will see you all in the next video.